impedance, you have to plot it. It's normalized, right? Normalized load impedance. And it can fall either inside the one circle, and if it does that, if it's inside the one circle, anything we add in series or any impedance we add to it will never put it to the rim of the one circle. So we go to the admittance domain. Y'all hear me on this, guys? So we go to the admittance domain. Now, if we're in the admittance domain, that would be inside the rotated circle. And there, we're going to find out an admittance that would allow it to get to the rim, either a positive or minus J to get to the rim. You all follow me? Now, because we're in the admittance domain, it's normalized. If it's a positive J adding, be a capacitor. If it was minus J, it'd be inductor. Y'all follow me on this?
And that is what is in parallel, correct?
Right. That would be in parallel. Then, after that, you get to the rim of this rotated circle, and you come and go back to the impedance domain, which is just 1 over the admittance. So now you're over here, and you got to see what you have to add in series to get rid of you could say the remnant J term, all right, the plus or minus J something. You're going to add the opposite value of that to get rid of it. So you'll have a value of 1, and that puts you right at the center, and that means your impedance matched. Now that's if the thing lands inside, your normalized impedance lands inside the one circle. If it's inside the rotated circle, right? Well, what happens? Where do we want to go on this?
The middle.
We want to go to the rim, right? So if we're inside the rotated, what do?
Add something parallel?
Well, oh, you're going to take it, man?
I suppose.
All right. Well, it would be series, wouldn't it? If you think about it, right? You all with me? It'd be a series impedance to get to the rim, right? Because now we're going to have plus J or minus J. This is an impedance, right? Mm-hmm. We got something inside here, so then we get to the rim. Take 1 over that. Remember, you're adding in series. Now you come over here. Now you're in the admittance domain, right? It was impedance, now this rotated circle is the admittance, right? And there you find out the value and you have to add whatever the J value is, you've got to get rid of it. So it's an admittance, right? And then the other way to do it, y'all, everybody with me on this? This is the standard stuff. What happens if you get one where it's outside of both?
You can do either.
Then it's up to you, you know? If you want to, you can, I mean, what I do, if I'm outside of both of these circles right here, I know adding a series impedance will never put me on a one circle, right, if you're outside of both. So what I'm going to go is go to the admittance domain, right? Then I'm going to add something in parallel, get to this rim, go to the impedance domain, add something in series to get rid of the impedance. That's what it is. But if you think through it, it's not hard. That's to be clear. Go ahead, Jim.
I was just wondering if this rotated Smith chart method was only for microstrips or can be used for the other transmission lines.
Anything that you have that has a transmission line or a waveguide matched to an impedance, like an antenna or something else, something where you know the characteristic impedance of something and you've got a line, that's characteristic impedance on a line, either transmission line or waveguide, and you want to make sure you don't get any reflections. You don't want reflections. I can tell you that's the thing that'll kill you. Then you have to do some sort of matching. I want to make one other point about this. This matching is only for a certain frequency. You follow me on this? So if you're talking and you're going to get into stuff, some of you in the real world, where you have wide band systems. Wide band is, you're not just a little bit off the frequency. That means a large, fairly large modulation index where you're going to have typically FM modulation on something, and if it's wide band, then the method I'm showing you here, it falls apart. Then if you're going to do matching, it's a different type of matching you need to do, and we haven't covered that yet. Y'all follow me on this class? So just be aware, this is for one frequency, narrow band. The wider, and matter of fact, how many looked at the tool I gave you, the calculator device? All right, that tool shows you things for high pass, low pass, and it'll actually show you the circuitry that comes with it. That's the stuff you would use if you had a wide band application. Some of you will work for companies where they're going to task you, not usually as soon as you get there, but after 3 or 4 years, they're going to be giving you things where you know about them, but you don't know everything about them. So just remember what I tell you, because some of you are going to find yourself in a position where I'm not sure how to do this, but I remember a professor saying that this stuff's only for narrowband, so I need to look at that tool that he gave me or something and go ahead and research it. And a lot of stuff, I'm going to level with you too. You start reading stuff on the internet. There's a lot of good stuff on YouTube and stuff like this, and Google, you can find all sorts of stuff. But there are things that are just bogus, and I've seen them out there. People trying to do something in engineering, and unfortunately, maybe their heart was right, but their method was completely wrong. Has anybody ever seen that on YouTube? This stuff? Boy, I have. I've come across it, especially when I teach an eMag and somebody hands in something that, where the heck did you get this? And either they paid somebody on Chegg or whatever it is to do it, and they didn't know what they were doing, or they were looking at things that were completely done wrong. And that happens. Okay. Now today, is there any more questions about the prior stuff? Anything at all? Yeah, go ahead,
Just
Tyler.
one quick question, sorry for repeating. Just to make sure, clarify, when you're going from the impedance to, like, what's it, the left, that would be parallel,
Admittance, it went over impedances admittance. You just take the normalized value, take one over it.
and that'll be parallel for that?
Well, you're asking, in your mind, it's clear. If you're in the impedance domain, 1 over that's the admittance domain. Now, if you're adding admittance, it's always in parallel. If you're adding impedance, it's always in series.
Okay.
All right, but in either case, it doesn't matter. We either add impedance first or we add admittance. So we're either going to add series element first or we're going to add parallel. And it's an L, they call it an L network because there's one going this way, one going this way.
Okay, so in the impedance domain, if you add positive J, then that's an inductor. If you add minus J, it's a capacitor.
Absolutely.
And then if in the admittance domain, if you add positive J, it's a capacitor. If you add negative J, then it's a inductor.
That's right. Go ahead.
Okay, cool.
In terms of the actual physical L circuit, is it when do you put the parallel component in front of the series component, and when do you put the series component?
Well, what does it always boil down to? If you're adding admittance or impedance, right? Maybe we should do one because that question tells me it's something not absolutely clear. You guys got one for me? I gave you a whole bunch. You can make one up.
I have one.
Oh, there's you gave us a time for the class.
Go ahead. You have one? Ben?
I can make one up for you. Off the top of my head.
We worked on one that you gave us at the end of
Sure.
Friday. It
Sure.
was,
I'll tell you what, this is one that they've actually thought about it. It's better to answer.
Yeah.
Whatever you add
to get back up to 0.
What do you?
Is that 0.2 plus
What is it?
0.8J?
Oh, yeah.
0.2 plus 0.8J?
ZL is, oh,
That's the
normalized.
normalized.
All right,
Yeah.
so small ZL, 0.2 plus J, 0.8?
Yes.
Okay, I'm going to try to sketch freehand a rotated Smith chart. Now, you guys are going to just have to forgive me for not getting it right. So this is the one circle, right? And this is the rotated circle. And now we've got a value of 0.2 plus J.8. Well, I know 0.2, the trajectory for 0.2 is something like that, isn't it? Correct? So, and where's point, when I'm on that 0.2 trajectory, and this is, just a rough sketch. Where is the, 0.2, where is J.8? Is it up here?
It's right there, yeah.
Yeah, so it's outside both of them, right? So I'm out here and I'll call that 0.1. Now, let's think about this. I'll put it right here. That's 0.1, right? Now that's ZL. Just think about this logically. I'm not drawing this very well. No matter what I add in series impedance to change the value of the J component, I'll never hit this one circle. Do y'all see this? This is the critical thing. So we go to the admittance domain. You with me, everyone? Anything we add in series, we can just get rid of the j. It's 0.2 plus, and I got j.8. So I could get rid of j.8. I still got 0.2. It's not doing me any good, right? So what I need to do is add something in the admittance domain, right? And how am I going to do that? Well, now I'm going to come over here and get the admit. You're going to have to help me with this one. What is 1 over ZL here?
0.3 minus J, 1.18.
All right. With me? Now which way do you want to go? Well, we want to go to the rim, right? So what are we going to do?
You got it.
Well, I'm going to do what? I'm going to go from here and I'm going to add something to get to this rim. Now this is minus j 1.18. If you go on the trajectory, you got to go on that r equals 0.3 circle, the large arc. Find out where it intersects here, and there'll be a conjugate point here that intersects. Y'all understand that? I call them trajectories. It's the circle, the arc equal 0.3 circle. But it's going to hit it. You ask me about this is a good problem. Makes you think. So down here, what's the value? Now, in either case, what are we adding? We're adding a positive value, J, aren't we? Correct, class? So positive J to here and positive J to here. But what's the value to get to here? Remember, we're in the admittance, right? But just tell me, can you just
Value to get there or the value?
well, what is the value of the point for starters?
0.3 minus J, 0.48.
Minus J 0.48. Is it, you all agree with that? All right, that's one of them. The conjugate point is going to be the same real part, 0.3, but it'll be plus J 0.48, right? So the conjugate point up here will be 0.3 plus J 0.48. Remember, that's admittance, right? Now, here's where you think ahead. If I add something in parallel to get to here, then when I go from the admittance to the impedance domain, I'm here, right? Y'all hear me on this? Now listen, now we're in the impedance domain, and we want to get here, so we're going to have 1 plus J, we have to add a minus J. That's a capacitor. Do y'all hear me? That means I would be adding a capacitor in the impedance domain. I don't want to do that because it blocks DC. And I can tell you right now, the thing I'm going to ask about is I want something that doesn't block DC. In other words, an inductor would be in series and a capacitor in parallel. Y'all follow me? So this point won't work if I want that. I need to go all the way up to here. So that means I go from 0.3 minus J 1.8 all the way up to here, which is 0.3 plus J 1.48. So the total distance would be what? 0.48 plus 1.18. Correct, class? Y'all with me? Ben, is this helping? All right. Nathaniel, I want to make sure you guys understand the logic. If you get this down, it doesn't matter what I get. You got it. All right. So, what's the total value yet? I'll draw this thing. So here's my normalized ZL, 0.2 plus J 0.8. That's an impedance. So this is ZL here. Now, I come over, and I'm going to put a parallel element. It's an admittance, and the admittance is what? J what?
1.66.
Yeah, that looks, is that right? Yeah, yeah. 1.66. Do y'all agree with that? It's a capacitor. We'll worry about the value in a second, right? Now I'm at this point, right? Somebody help me with this. Jack or Jake or William or Ben. Now I'm at this point. Now I need to go. That would be from point. This is point 1. This would be point 2. This would be my point 3, not that one. Y'all with me? Now I need to go to the what? The impedance domain, correct? So I take 1 over that. Can you just tell me what that is? It better be 1 minus something J. If it's not, we messed up. The real part will always be close to 1. Go ahead, Ben.
I got 1 minus 1j, or j1.
1 minus J1. Sounds good. Y'all follow me?
Is it 0.3 plus j 0.48 that we're doing?
All right, you take 1 over that.
Yeah, I got 0.936
Yeah, I-
minus.
Okay, wait, sorry, I thought we were doing
1.49
from
J.
3 to,
We're going from 3 to here, 4.
4.8 is wrong on that edge, 0.46. I misread this.
4.6, sorry. So what do you get for this?
And then whenever I go back across with 0.3 plus j, 0.46, I get 1 minus 1.5j.
That's what I have as well.
Okay, that's right. Now, I need to add a plus in series, an impedance of plus J1.5. Agreed? That would be an inductor. I'm just going to put it in. J1.5. Notice they're both positive. That's an impedance normalized. That's an admittance normalized. So now for the values, what do we know? If you want the values, and I'll ask for values, you've got a certain frequency. Say it's 10 to the 9th hertz, 1 gigahertz. It's a reasonable frequency. It's a microwave. It's a lower microwave, but it's microwave nevertheless. A lot of work goes on these days, at least in my world, between about 1 and 80 gigahertz. All right, and now with automotive radars, there's 77 gigahertz, a lot of them. There's a ton of stuff that goes on. And this microwave engineering stuff, I mean, the things we're showing you here, that's something that's done regularly to match. If you have an antenna or something like this, it would be narrowband for automotive radar. Yeah.
So does it matter which order the series and the parallel component? So like, could you put the capacitor in parallel and then the inductor, or is that going to be, would that
The
change?
capacitor has to be in parallel.
No, I'm saying, could the capacitor be before the inductor?
Well, wait a second. You talking here?
Yeah.
That would make no sense. You'd add an impedance first, wouldn't you? Just take that out. You'd be adding a series impedance, which makes no sense.
Doesn't matter.
Yeah, it really does matter, yeah. And you better believe it matters. You've got to have admittance first in parallel, then series inductance, or else the whole thing falls apart. And I could almost see somebody in a lab messing that up. All right, so if this is F is 10 to the 9th hertz, now let's get the actual elements. Let's go ahead and get this one first. All right? That's admittance normalized. We know it's a capacitor, right? So in general, the admittance of a capacitor is 1 over the impedance. So it's just J omega C, right? That's the admittance, correct? And if it's normalized, we multiply by Z naught, don't we? So we multiply by Z naught. You can get, just get the normalized impedance, 1 over J omega C divided by Z naught, and then take 1 over that. That's the normalized admittance. Everybody okay? All right, we have that. We know the value. I mean, this is 1.66. Therefore, if we want C, I got to give you a Z naught. I'll tell you the truth. Z naught is almost always 50 ohms for microwave work. Now, it's different with Charter or Spectrum or whatever the cables. It's about 75 ohms for those cables. And there's a reason for that. It has to do with the breakdown strength and things like this. Typically, for microwave work, if you're building things, 50 ohms is a standard used for everything. You buy stuff that's standardized, 50 ohm cabling, 50 ohm everything. All right, so if I wanted C for this, what happens? Well, I just take 1.66, right? And divide it by omega, divided by Z naught, and lo and behold, I have my C value. For ticks, what is that? If I say Z naught is 50, omega is 2 pi f, right? So it'd be 1.66 over 100 pi times 10 to the 8.
Around 5.28 picofarad.
5.28 picofarad. That's a small thing, but it sounds right. Is that right, guys? All right. So that's the capacitor. Somebody, not me. How do we get the inductance value?
it's going to be,
Well, let's go through the math first. What's the formula? You take the inductance, the impedance of an inductor is J omega L, right? And what do we do next?
you,
Normalize it, divide by Z naught, right? And then we set it equal to J1.5. And I think you guys got it. If I want L, At 5 line L, it's 1.5, right? Times Z naught over omega, correct? What do you get for that anyway?
11.9 nanometers.
11.9 what?
Nanohenries.
Nanohenries, okay. Now that's small. I want to tell you, those values are small, but they're available. And one of the things you're going to find when you're doing this is telling you, a lot of times, a 1 or 11.9 nanohenry component may not be available. So you would probably get a 10 nanohenry, and then you would just mess with the lead links a little, so you added that extra bit, and you can measure the impedance of that with some of the spectrum analyzer. What you can do is, this would be more laboratory work, but you can measure these things with, I'll say, good equipment. You know, have you worked with network or spectrum analyzers? Yeah. You all know when you have an oscilloscope, that's a very high input impedance, correct, class? And if you want to, what you can do is you can just have a simple resistor inductor bridge. And you know, if you want the value of this inductive reactance at a certain frequency to be exactly equal to the resistors, half the input voltage will appear across that inductor. Follow me? Well, that's actually not quite true. It's going to be 1 over square root of 2 times it, because they're out of phase by 90 degrees. But anyway, you know the value of that. So what you'll do is start adjusting the lead length until you get exactly half that voltage. That's the trick. And you know what you're going to do, I don't want to do this, but when you have inductors, you'll have a coil of wire, small little coil, then you'll have these leads. Well, if you just measure the full inductance of that with the leads, it's going to be greater than the actual inductance measured. Chances are much greater. Then you have to start cutting down the lead length a little bit, but you start small, but that's how you do it. All right, any other questions about this? Yeah.
You mentioned something about dodging the DC.
What's that?
You said something about dodging the DC.
Well, we want to make sure we allow DC biasing, because this load could be the base of a transistor. You all know BJT transistors require current to bias them, right? Well, in order for that current, that DC current to flow, you would want an inductor in series and a capacitor in parallel. If the inductor was in parallel, it shorts out the DC. Y'all follow me? So, in general, when you're doing this stuff, inductor in series, capacitor in parallel. Unless there's some overwhelming reason why you would want a capacitor in series. Generally speaking, you don't do that. Okay. Now, today's topical stuff before the quiz is going to be on S parameters. Now, we've got about 2 weeks left, I'm told, and I believe, before final exam week and all the fun begins. I mentioned this earlier, that I don't know the date of our final, but if everybody wanted the final change, I can have that happen. I've done it before, because I was asked by students, a whole bunch of students, and I didn't even know that was an option. I checked with the provost office. In fact, it is, but it has to be an ask. All right. And if you want to move, just think about it. You guys are good at discussing this, apparently. Chat amongst yourselves or on whatever the tools are, grouping it, and just find out if you would prefer it at a different time and date. All right? Shan, here's the reason. I keep hearing it. Apparently, the contracts expire before the finals are over for a lot of apartments. Is that right, or am I wrong?
That's for.
I've heard this, that they have to be out of apartments before, like the end of April or something.
It depends on your.
That's at the end of the summer. That's for the summer term.
It's summertime? All right. Well, I don't know all the things. What I'm doing is trying to be as accommodating as possible to you. If you don't want to change, it's not a problem. Now, this is going to be S parameters. Write this down. These are important. And this all has to do with microwave engineering. When we talk about S parameters, what we're doing is looking at something as a black box. We don't know what it is inside. We just know what it does from the outside. So we'll start by saying we have some transmission line here with a characteristic impedance Z naught. And there's going to be information going. There's going to be some V1 plus information propagating that way. And there's going to be some reflected information, V1 minus. Now that V1 is developed across the transmission line from the plus to minus lead, but it is a wave traveling that way nevertheless. You all follow me? Now we put in this thing, and it's just a box. Something is in here that's being connected to this transmission line, and this is called port 1. It's where the information is coming in, and then there's going to be port 2. And here, there's going to be another transmission line. And we can assume, if nothing else is said, that this thing is matched into a characteristic impedance of Z0, so there's no reflections. And there will be a wave also, possibly, of V2 plus, and something coming out of that port, V2 minus. So there's waves going into port 1 and into port 2, and then waves coming out of port 1 and port 2. You all follow me on this? So this is sort of like the place where it actually all happens right here. And this has what's called S parameters. So the relationships between the voltage, these be phasor voltages, V1 and V2, are this. V1 minus is equal to S11 times V1 plus S12 V2 plus, and V2 minus is equal to S21 V1 plus S22 V2 plus. Now these voltages, V1 plus, V2 plus, they would have values like 10 at an angle of 30 degrees. It's at an assumed frequency. This is not something where you're doing transients on. Y'all follow me? This is going to be stuff we're at a constant frequency to do this. And I had a lot of fun with it. I mean, I learned a lot about S parameters when I was at NASA doing stuff where we're trying to measure things using, this is called a two-port system. We were measuring the S parameters of things and then figuring out by a reverse engineering process. We used a first sequential quadratic program, then we used a global optimization program called genetic algorithms we used to optimize this, then figure out what the actual values were of the material properties. But I don't want to get into it. Just telling you I've had experience with this, it's very important, and you will too. So when we do this, that doesn't mean much to you until you see how we actually use this to find S parameters for something. And you want the S parameters for everything. They're functions of frequency. So the best way is, that's what's going on, is for me to just give you and show you a problem. Okay? So, well, first of all, let me say this. When we take a look at this stuff, this doesn't make a lot of sense. But what I can say is the port 1 reflection coefficient, which would be V1 minus over V2 over V1 plus, pardon me, can be gotten if we assume that V2 plus is equal to 0. Now just think about this. If I have V1 minus over V1 plus, well, that is the reflected signal at port 1, is it not, class? If V2 is 0, so we assume there's nothing there happening. Y'all with me? Here, if we look at this, and by symmetric arguments, you could say, well, if I have V2 minus over V2 plus, with V1 plus being 0, that would be the reflection coefficient of port 2. In fact, it is. So, this is a symbol for reflection coefficient. Is going to be V2 minus over V2 plus, with V1 plus being equal to 0. People normally just associate with that. There's no source over there. That's sort of true, but the problem is if you put a short over here and you have things coming, it'll hit and come back, so you will have a V2 plus. So we'll have to look at that more carefully in a second. Now, what about S12 and S21? Well, the way you're going to get that, if I wanted S21, that would be the ratio of V2 minus over V1 plus, but this would assume that V2 is 0. I'm going to talk about this for a second. Y'all follow me on this, class? Go ahead, take a look. If I wanted S21, I have to make V2 0, don't I? V2 plus, pardon me. V2 plus 0, right? And then, if that's 0, then I can just see S21 is really the ratio of V2 minus over V1 plus. I want you to think about it. I got a signal coming in, V1. I got a signal coming out, V2 minus, right? Well, the ratio of those two would be called the gain if it was a voltage ratio and you had a voltage amplifier, a standard BJT or an op-amp. You all with me on that? So that's something that makes sense, right? So S21 is like the forward gain. Y'all follow me? And you can call it the forward gain. The forward gain. Now, if you want the opposite, the reverse gain, like if I put a signal in here, how much signal gets out here? The gain is a loose term. It probably decreases the value, but they call it the reverse gain. When I look at this, S12, well, what does that equal to? Here's S12, it would be V1 minus, right, over V2 plus, assuming that V1 plus was equal to 0. Y'all follow me? With me on this? Now, it's still pretty abstract until you see it applied. So these are called S parameters. When you did your circuits, did you have H parameters, or I should say your transistors and stuff, your microelectronics, you had H parameters? You had GM, right? You remember that? Because of transconductance, did you have H parameters? All right, H parameters are just like this. You can get, from H parameters, you can get S and vice versa. You can also get, there's a variety of different things, but this is the most standard way to teach this because this is the way it's done with microwave engineering. Forward gain, reverse gain, in both directions. So the best way to do this is start with an example and solve for something. Here's the best example I can think of. Wentworth doesn't do this in his book. He starts a little differently. I'm going to assume I have a characteristic impedance right here, 50 ohms. And then this is going to be my port 1. And the only thing I'm going to do is put a resistor here. Make that resistor 100 ohms. All right? Then I'm going to connect it to another transmission line. And this is going to have a characteristic impedance V0 equal 50 ohm. And it will be into a matched load. All right. So the load is 50 ohms, right? Now the only reason I did that is now nothing's going to be reflected. If something gets through here and hits, it doesn't reflect back. It's called a matched load. Y'all follow me on this? Whenever you hear the term matched load or matched port, it means V2 plus is 0. There's nothing coming back. That's all it means. So let's go ahead and get the S parameters of this. I'm going to do it over here. When I take a look at this, the first thing I usually go for is a reflection coefficient right here for port 1. That would be equal to simply, I didn't put this down, that's S11. I'm sorry I did. This is S22, isn't it? By definition. Right, so when we talk about reflection coefficient on port 1, it's S11. Reflection coefficient on port 2 is S22. And by the way, there's N possible ports. With radar, 3 or 4 port devices are used all the time because we have signals coming in, they come in from one way, they route the other way, and vice versa. If something comes into this port, it routes to a different port. So we have a lot of this kind of stuff with radar work. All right, let's get S11. All right, I want the reflection coefficient at port 1, S11. Well, how do I get it? Here's port 1. I want you to just think about this. If this is a transmission line problem, and I'm looking for the reflection coefficient here, what do you always do when anybody talks about reflection coefficient? You look at the impedance you're going into, right? And you subtract it from the impedance you came from, and then you divide by the sum. Y'all remember that? So what's the impedance you're going into? I gotta make sure you see this. Well, I got 100 ohms here for sure, right? And then I got an additional 50. Now that's matched, all right? So it's just 50 ohms. You all see this? So I'm going into 150 ohms. I came from 50. So that means S11 here would be equal to 150 minus 50 over 150 plus 50, or it would be 1/2. Do y'all agree with that? This doesn't have to be here because S parameters don't have to do with the loads. I just wanted to show you that. All right. Now, can you see the rational argument why S22, or the reflection coefficient of port 2, would be the same? Isn't this circuit identical if I look at it in the forward direction or the reverse direction? Y'all see that? Now, we could go ahead and say, well, I need the impedance going in there. It'd be 150, right? And the impedance I came from, by definition, is 50. So when I take 150 minus 50 over 150 plus 50, I get the same thing as S11, and I get 1/2. Y'all with me? Now, the next part's the one you pay attention to because people mess this up. So I want to make sure you see this. We're going to go get S21. Now look at that. It's a ratio of V2 minus over V1 plus, right? I'm going to do this over here. So when I think about V2 minus, here's one of the big problems people have. Remember, this has got a characteristic impedance of Z0, right? So if I have V1 coming in here, when it hits, at the instant it hits, it creates a waveform that's going to reflect. It would have the value of gamma times V1, right? And the superposition of that V1 plus gamma V1 plus would be equal to the voltage on the other side, right? It's not equal to V1 plus is what I'm getting. So the voltage right here, and I'm going to call it V prime. We're taking a look at a wave propagating this way. V prime, that's the voltage just on the other side of this transmission line, would be equal to the transmission coefficient, tau, 1 plus the reflection coefficient, times V1 plus, or it'd be 1 plus the reflection coefficient of port 1 times V1 plus. Do y'all follow me on that? So in our case, what do we have? Well, I had V1 coming in here. Over here, I have 1 plus gamma. Gamma was 1/2, so it would be 3/2 times V1 plus. Do y'all follow me? Right? Take a good look. So this is going to be equal to 3/2 times V1 plus. Now that's the voltage just on this other side. Here's the transmission line. Now we're on the side there's no transmission line. But that's not the voltage that gets out. We have voltage division, don't we? Because there's 100 ohms in series with 50 ohms. The amount of voltage here will be 50 over 100 plus 50 times that income. So then, that's my V prime. Now I can say that my V2 minus would actually be equal to V1, this voltage here, V prime, right? And then it's going to be times 50 over 150, or 1/3. So really I have V2 minus equal to, and this is going to be 3/2 times V1 plus times 1/3, or it's V2 minus over V1 plus is equal to simply 1/2. Now you're going to take a look at that, and that would be S21. Do y'all see that? This is in the book. I want to make sure you see this. This is the way we get the forward gain. So whatever's coming in, half of it comes out as far as voltage. Y'all follow me? How many see that that would be the same thing for S12, the reverse gain? Output voltage versus input voltage. You better believe it. It's symmetric, isn't it, class? So that's how you use these S parameters. Now, I didn't do a lot of examples. I'm going to give you a quiz, but I'm going to give you homework on this. And I want you to work on it because this is so important. But there'll be places you get confused. Don't worry about that. I'll take care of that on Wednesday. All right. Now for the quiz. Can we do something, I've always spread people out. How about this first row